Hi everyone. So my name is Basil Peter. Now you're actually watching Basil's physics classroom. Now I'll just give you a brief introduction what you're gonna see in this channel. First of all, rotational dynamics is one of the most important chapters for your NEET entrance examination or your JEE entrance examination. So we'll be starting with that. In the previous year and the year before that, if you see, you are getting close to 3 to 4 questions or sometimes 2 questions. And in JEE, surely you'll be getting 1 question guaranteed from rotational dynamics. So we'll be dealing with the basic concept that has to be covered in rotational dynamics. In our other videos, I'll also be discussing supporting problems for that. Okay. So talking about rotational dynamics, the chapter rotational dynamics can actually be divided into mainly 4 parts. First part I will be talking to you about will be about the center of mass concept. Center of mass. The second part I'll be dealing with moment of inertia equations. Which one? Moment of inertia equations. In the third part, we'll be dealing with some chota equations which are very essential and which from where you're bound to get 1 question guaranteed. So chota equations. Chota equations. And after that, towards the end, you'll be learning about rolling motion also. Rolling motion. So this is a major 4 categories you have to cover in rotational dynamics, or as you call in your NCERT, system of particles and rotational motion. Okay, so let's start off with center of mass. So center of mass, that's a very common term which you might have already heard, and you have already learned that in a much detail in your schools about center of mass. Now I have seen students balancing their books on a finger. They are able to rotate the books on a finger. I think you might have also done it. Okay, so what is making them balance a book? Have you ever thought about something like that? Now center of mass means, suppose we have a car and we want to analyze each and every single part of a car separately. Now, as you know, a car is composed of n number of parts. So analyzing each and every single part will not be an easy task. Say for example, we need to specify the speed of a car. It's not easy to specify the speed of the steering wheel, the accelerator, the dashboard, the seat, everything. It's not a easy task to do that. So you know what we do? We specify a point inside the car where we assume that the entire mass of the car is concentrated. I repeat, we are assuming a point where the entire mass is concentrated. Friends, that point we call it as the center of mass. That point we call it as the center of mass. So center of mass is the point where the entire mass of an object is assumed to be concentrated. Okay. So when you talk about center of mass, first let me deal with the 2 particle system. So consider a mass m1, another mass m2. This is the Cartesian coordinate system in drawing. We have the y-axis, we have the x-axis from the origin. M is at a distance of say r1, and from origin m2 is at a distance of say r2. Okay, so r1 and r2 represent the position vectors of m1 and m2. Okay, so we only have 2 masses there. It's a 2 particle system. So we need to specify the center of mass. We can call it as RCM. The center of mass of this 2 particle system is given by RCM is equal to m1r1 plus m2r2 divided by m1 plus m2. Right? I'm very sure that you're very familiar with it. Now, one thing you have to remember about this RCM is, this RCM actually contains 3 components. One along the x-axis, the other along the y-axis. Here it's a 2-dimensional figure I've taken, but in real life it is a 3-dimensional motion we are observing. So we need to specify z-axis also. So RCM is actually equal to xCM I cap plus yCM j cap plus zCM k cap. Right. So we have specified the center of mass of a two-particle system. Now suppose we are not talking about a two-particle system, instead we have a n-particle system. How do you specify the center of mass? For an n-particle system, the center of mass RCM can be written as RCM is equal to M1R1 plus M2R2 plus etc. till MnRn divided by M1 plus M2 plus etc. till Mn. So we have specified the position of the center of mass of an n-particle system. Remember this formula, this might come in handy. Okay, so the questions come from this portion are generally easy, but we can solve it only if you understand this concept of center of mass. Okay, so now you have the position here. So once you have the position, you can specify the velocity also. How do you specify the velocity? Vcm is equal to, just imagine that you are taking the derivative of this. What do you get? m1 v1 plus m2 v2 plus etc. till mn vn divided by m1 plus m2 plus etc. till mn. So we have the velocity of the center of mass. Okay. Now moving on to the acceleration of the center of mass. ACM is equal to m1a1 plus m2a2 plus etc. till mn an divided by m1 plus m2 plus etc. till mn. So we have specified the position of the center of mass of a two-particle system and that for an n-particle system. Now, since we have written ACM here, we can also apply Newton's second law, right? So let's apply that. So we can write the force acting on a system can be written as F is equal to M into ACM. M into ACM. Now, ACM, how can I write acceleration? Is it related to velocity? Yes, it is the rate of change of velocity, acceleration, right? So we can write like this, M into dVcm by dt. Now suppose we have an isolated system and the net external force on it is 0. Suppose we have an isolated system and the net external force on it is 0. How do you write? If F is equal to 0, that implies what will be Vcm? There can be only one possibility, right? Vcm should be equal to what? It should be a constant. Vcm should be a constant. Vcm is a constant means the velocity of the center of mass is remaining a constant for an isolated system on which the net external force is equal to 0, right? So now, talking about center of mass, we need to remember some major important properties about it. The first property I would like to mention is, for a uniform mass distribution, I repeat, for a uniform mass distribution, center of mass and the geometric center will be coinciding. Say for example, we have a circle. What is the geometric center? Yeah, the point where the diameters meet, right? So this will be exactly the center of mass also. What is the center of mass for a square? The points where the diagonals meet. That will be the center of mass also, if it is a uniform mass distribution. Now, if it is not a uniform mass distribution, how do you find the center of mass? To find the center of mass in case of a non-uniform mass distribution, we have this condition, RCM is equal to integral R dm divided by integral dm. For a non-uniform mass distribution, from one end to the other, we can take the integral, apply this condition and find where is the position of the center of mass. Okay. Now suppose we have a non-uniform mass distribution. I told you how to find it. And now one thing to remember is, in case of a non-uniform mass distribution, the center of mass will be always closer to the heavier mass. Repeat, in case of a non-uniform mass distribution, center of mass will be closer to the heavier mass. Okay. Another important point worth remembering is, suppose we have a ring. Okay, suppose this is a ring. Okay, this is a ring, as you can see it. Now, where is the center of mass position? It is a uniform mass distribution. Let's assume it's a uniform mass distribution. Where will be the center of mass? At the geometric center. Alright. So at the geometric center, tell me, can you see any physical mass here? Is there any physical mass present here? No. Which means at the point where we choose the center of mass, there need not be any physical mass present there. There need not be any physical mass present there. So remember, that's point number 3. And now one more point. The center of mass depends on the shape of the body and the distribution of masses. Center of mass depends on the shape of the body, distribution of masses. Remember that. Center of mass depends on the shape of the body and distribution of masses. Okay. So we have discussed the major points you have to remember in the concept of center of mass. And one more thing. Suppose you are told that a system is in equilibrium and you have a two-particle system. Like the one I previously drew. You have a two-particle system. This is R1. This is R2. M1. M2. This is RCM. Okay, fine. Now, suppose you are supposed to find out the moment of the mass about the center of mass. Suppose you are asked to find the moment of the center of, the moment of mass about the center of mass. How do you find that? Now, remember that M1 into, if the system is in equilibrium, plus M2 into R2 minus RCM should be equal to 0. So remember this condition. Okay, so moment is a term which you will be seeing more frequently now. The next section about the moment of inertia, we will be learning about moment of mass in much detail. Okay, so shall we move to the next session? So I hope the center of mass portion is clear for you. So we are moving on to the next session now. That is about the moment of inertia. Okay, so moment of inertia. So what do you mean by moment of inertia? Now, inertia is a term which you are very familiar with. When you are moving in a bus, when the bus suddenly stops, you fall forward, right? Now, similarly, when the bus starts suddenly, what happens? You fall backward. Now, that is because of inertia. Inertia of rest is there, inertia of motion is there, inertia of direction is there, and all those things you are very familiar with. Now, right now, what I am talking to you about is moment of inertia. Moment of inertia is actually related to rotational inertia. Now, you might have observed, when you switch off a fan, what happens? Does the fan suddenly come to a stop? It does not. Why? Because of inertia. So, inertia, or the moment of inertia, we can say, in a way, we can define it as, it is the inability of an object to stop or start its rotational motion upon the removal of an external force. Okay? Or without the aid of an external force, the body is unable to start or stop its rotational motion. That is what is the basic idea about moment of inertia. Now, we don't need all these hefty definitions and everything. We are going straight to the point. So, in case of moment of inertia, which is represented by I, now one thing you have to remember is it is not a scalar or it is not a vector quantity. It is something known as a tensor quantity. For a point mass, the moment of inertia is given by I is equal to mr square for a point mass. If the shape is defined, the moment of inertia will have a different value. Okay? And for a continuous mass distribution, the moment of inertia can be written like this. I is equal to integral r square dm. Moment of inertia is equal to I is equal to integral r square dm. Another important point you have to remember is it depends on the shape, the mass, and the position of the axis of rotation. And the position of the axis of rotation. So it depends on the axis. It depends on where the axis of rotation is. Say for example, in your fan, the axis towards the center. Right? So similarly, it depends on the position of the axis of rotation. Now, let's see what is the moment of inertia of some commonly observed bodies, which usually comes to our examination. The first thing, is a ring. I'm going to show you. For a ring, we can correlate it a lot, okay? So that will be easy to remember. For a ring, through an axis through its center, the moment of inertia is given by mr square, where r is the radius, m is the mass. And through its diameter, the moment of inertia I will be equal to mr square by 2. Okay? Now imagine I'm placing one ring over the other. I'm placing one ring over the other. What do you get? Placing one ring over the other, you'll get a hollow cylinder. And remember that for a hollow cylinder and for a ring, along its geometrical axis, the moment of inertia is the same, mr square itself. No change. For a ring and a hollow cylinder, I repeat, for a ring and a hollow cylinder, along its geometrical axis, the moment of inertia will be mr square itself. Now suppose we are having a transverse axis, a perpendicular one. For a cylinder, the moment of inertia for a hollow cylinder is given by I is equal to m into L square by 12 plus R square by 2. Okay, so we can relate a ring and a hollow cylinder and you can learn it easily. Clear? The next one I'm moving to is a disk. So for a disk, how do you write the moment of inertia? Again, we can specify moment of inertia along two axes. One along the geometry axis here, and this will be equal to mr square by 2. Okay, you don't need to go into the derivation part of this. Okay, so I is equal to mr square by 2. In the ring it was mr square, in a disk it is mr square by 2, and along the diameter it will be mr square by 4. Now imagine you're placing one disk over the other, stacking them together, one over the other. What do you get? You get a solid cylinder. Okay, and again for a solid cylinder, along this geometrical axis, it will be mr square by 2. And along the transverse axis, it will be m into L square by 12 plus R square by 4. So we compare a disk and a solid cylinder. Clear? So we can correlate them and we can learn that. The next one we are going on to see is about a sphere. And the sphere, cylinder, ring and everything is commonly asked questions. Whichever entrance exam it is, whether it be NEET or JEE or whatever you're writing, that will be some common questions you can expect. And without knowing all these equations, you cannot go forward. Okay? And for a sphere, now remember that in the question, if it is just mentioned a sphere, they're actually referring to a solid sphere. And if they've just mentioned a cylinder, they're referring to a solid cylinder. Remember that point. Okay. For a sphere, it's a solid sphere I'm talking about. Along its diameter, the moment of inertia is given by 2 by 5 mr square. And for a hollow cylinder, it's given by, hollow sphere, it is given by, along the diameter, 2 by 3 mr square. So, if you take a sphere and if you're passing an axis through its center, all the axes will actually pass through the diameter only. Okay, so this is some common cases that we are coming for your exam. Now, a very important thing, that's for a rod. A uniform rod. For a uniform rod, thin rod, about a central axis, suppose the length is L, so about this axis, moment of inertia given by ml square by 12. And again for a square lamina or a rectangular lamina, I write first. Rectangular lamina, the moment of inertia is given by, to its center is given by I is equal to m into, will the side be A, the length is B, so m into A square plus B square by 12. Now suppose it is a square. If it is a square, what happens? A will be equal to B. For a square, so what will be the moment of inertia? It will be I equal to m A square by 6, because A is equal to B. Right? Now, the square can be expanded. How do you expand the square? And what do you make it? You can make a cube, right? So we can make a cube using a square. And for a cube, again the moment of inertia through its central axis will be given by ma square by 6 itself. Okay, so please remember all these basic concepts, basic equations corresponding to the different shapes I have taught you right now. Okay, now to apply all of this, you need to learn about two theorems, two very important theorems. Without that, you cannot go for your examination. Okay, the first one, parallel axis theorem. Parallel axis theorem. So what is parallel axis theorem? Suppose we have a lambda like this. I have an axis, and this I will call it as my ICM. That is the moment of inertia about the center of mass. I need to find out the moment of inertia about this axis. Okay, so how do you find out? So to find that out, I should know this perpendicular distance. This I'll call it as x. So according to parallel axis theorem, the moment of inertia I about this axis is given by I is equal to ICM plus mass is m, mx square. The moment of inertia about this axis will be equal to I is equal to ICM plus mx square. So to know the moment of inertia of this axis, you should know the moment of inertia of another axis ICM plus, and the perpendicular distance also should be known, plus mx square. So the application level of this is very important. We'll see some questions later on. Okay, so that is parallel axis theorem. Now the second theorem is perpendicular axis theorem. Perpendicular axis theorem. Perpendicular axis theorem. Again, let's consider a lamina. I need to find the moment of inertia of this axis, I. And now to find the moment of inertia of this axis, I should know the moment of inertia of two other axes. And those two axes should be perpendicular to each other, and they should lie in the plane where this axis is intersecting the plane. I repeat, these two axes, one I will call it Ix, this I will call it Iy, they should be perpendicular to each other. They should intersect at the same point at the plane. So here, according to perpendicular axis theorem, I can write I is equal to Ix plus Iy. A simple example for this. Suppose we are taking a ring, okay? Along the diameter, what is the moment of inertia of a ring? mr square by 2, right? And drawing another diameter here. This is also mr square by 2, right? You need to find out what this axis. Suppose you don't know this axis moment of inertia. How do you find out? According to the law, I is equal to mr square by 2, Ix, plus Iy, right? Plus mr square by 2. What do you get? That will be equal to, right, mr square. That's what you've already learned, right? So that is how we apply perpendicular axis theorem. Okay, so don't expect this question to come for your exam. You will actually get better questions than this. Okay, so we have learned about the two theorems, parallel axis theorem and perpendicular axis theorem. Now one more point to remember is about radius of gyration. When you move on to rolling motion and everything, this term is of high significance. Okay, so when you talk about radius of gyration, let me tell you what it is first of all. Now radius of gyration is actually the perpendicular distance. Perpendicular distance from where? Suppose I have an axis over here. It is a perpendicular distance of a point from the axis of rotation where if you take the moment of inertia, so I repeat once again, it is a perpendicular distance of a point from the axis of rotation. We will get a moment of inertia value which is same as the moment of inertia for a distribution of mass. Okay, so it's a complex definition, but you don't have to worry about it. The only thing you have to remember about a theoretical point of view, you don't have to bother about it here. So only thing you have to remember there is I is equal to whichever body we are taking, maybe it is sphere, it's a cylinder, it's a ring, whichever body you are taking, I is equal to mk square. I is equal to mk square. So suppose you are asked to find out the radius of gyration of a sphere. I already told you. If this mentions sphere means what are they referring to? They are referring to a solid sphere. So sphere, moment of inertia you will find out. Right? You already know that. So what is I? I is equal to 2 by 5 mr square. Right? But I already told you, for any body, any shape you take, moment of inertia is always equal to mk square. So how do you write it? I is equal to mk square. Right? So this is equal to 2 by 5 mr square. If it is a ring you are taking, you can write mk square is equal to mr square. If it's a disk you are taking, you write mk square is equal to mr square by 2, and so on. So here m and m get cancelled. So you get k is equal to root 2 by 5 r. Understood? So radius of gyration is a very important concept. You have to remember how to find the value of k also. Usually k by r or k square by r square value will be needed for you. When we come into rolling motion, you will see about that. Now one more thing in addition to this. Suppose we are having a mass m1 here, m2 here, m3 here. It's a distribution of mass. Okay. In such a case, we can write the moment of inertia, the total moment of inertia about the axis of rotation will be m1 r1 square plus m2 r2 square plus etc. till mn rn square. Now suppose you want to find the radius of gyration of that system. How do you find the radius of gyration? Now radius of gyration, you know it is equal to what? I is equal to mk square, right? So this m is actually the total mass. We can write that as n into m. If m1 equal to m2 equal to etc. till mn. So this is nmk square, right? Equate. What do you get? All the m's will be getting cancelled out since they are all equal. m1 equal to m2 equal to etc. till mn. So all the m's will be getting cancelled out. You will be getting k square is equal to r1 square plus r2 square plus etc. till rn square divided by n. So please remember this also. This has also been asked once previously. Okay. So these are the main important things you have to remember about moment of inertia concept. I hope it's clear. Okay. Shall we move to the next part? Right. So we'll move on to the next part, and that is about which one? The chota equations I told you about. Okay. Alright. So the first term I would like to introduce to you then, in the third part of the chapter is about torque. Torque. Now torque, we call it as a rotational analogous of force. We call it as a rotational analogous of force. In laws of motion, we are using force and we are learning about force. Newton is actually giving a very good quantitative, qualitative definition for force. Okay. So torque is actually the rotational analogous of force. Okay, I'm not going into much detail about it. We'll straight move on to the equation part, which is necessary for examination. So torque, it is given by, represented by tau. Torque is a vector quantity given by R cross F. Given by R cross F. So one thing you have to remember there is, this F, it is actually the tangential component of force. Say suppose this is an object. I will need to make it move in a circular path. What do you have to do? I should have a tangential force here. Okay. So even if I'm applying a force at an angle, say I'm applying a force like this, I can rotate it. But the tangential component of the force I'm applying is actually causing this object to rotate. Understood? So which means I can write torque is equal to R cross F, or if I draw a small object, this is force, tangential, this is R. What is the angle between them? It will be 90 degree there. So I can write this as torque is equal to RF or FT I will write. Or this can also be written as R into, what is force? According to Newton's second law, M into AT. M into AT. Now talking about AT, the tangential component of force, you have to remember that you have already learned about three equations, right? Equations of motion. V is equal to U plus AT, S is equal to UT plus half AT square, and V square minus U square is equal to 2AS. When you come into rotational motion, those three equations can be written in this form. 1. Omega is equal to omega 0 plus alpha t. 2. Theta is equal to omega 0 t plus half alpha t square. Third one, omega square minus omega naught square is equal to 2 alpha theta. So the three equations of motion I have written like this. And also one more thing, the distance traveled by the body in the nth second. Theta n is equal to omega 0 plus alpha into, what is that? N minus 1 by 2. Okay. So now, this alpha, that alpha we call it as the angular acceleration. We call it as the angular acceleration. Omega we call it as the angular velocity, and this is the final angular velocity. Omega naught we call it as the initial angular velocity. And here again another term is here, theta, that is the angular displacement that I have already mentioned, I guess. So theta angular displacement, omega angular velocity, and alpha is the angular displacement. Sorry, angular acceleration. So now, this omega can be written like this. It is the rate of change of angular displacement. And this alpha can be written as rate of change of angular velocity, similar to what we have learned in linear motion, right? Another way in which this alpha can be expressed is, alpha can also be written in terms of the acceleration as AT by R. Alpha is also equal to AT by R. Another important equation you have to remember, and you may get questions based on this. Okay. Now, another condition that you remember is omega. It's written as V by R, or V is equal to R cross omega, or omega is equal to V by R. Okay, so alpha is equal to AT. Now AT is actually the tangential component of acceleration. So A subscript T is a tangential component of acceleration. I'm going to use this result over here. So what do you get? Tau is equal to R into M into, it is what? Alpha R from here, right? M R into R, mr square. What is mr square? Yes, for a point mass. So torque is equal to mr square is I, the moment of inertia for a point mass, I alpha. So torque is equal to Rf, which is equal to I alpha, and this is a very, very important relation which you cannot forget. So for the shorter equations, I have taught you the equations for the rotational motion, the three equations, the four equations, and the small alpha is the relation for alpha, for omega, and also the condition of connecting this. This is actually an equation which has come for the examination previously, both for the NEET entrance examination and for the JEE entrance examination. Okay, alright, so that is about torque. Now moving on to the next term, angular momentum. And you already learned about momentum in linear motion, right? Momentum. We call it as a quantity of motion contained in an object. Now, angular momentum means it is defined as angular momentum. Angular momentum is defined as the moment of linear momentum. What do you call it? The moment of linear momentum. So wherever you see the system R, you can call it, expresses by the term moment. You call it moment of mass, and torque you can call it as moment of force. So this is moment of linear momentum. Now this can be written also like this: L is equal to R cross, right? How do you expand the cross product term? P sine theta. Right? It's a vector obviously. It is a vector quantity, this angular momentum. So again a circular path I am showing you. Velocity, which is tangential, R angle 90 I am taking. L is equal to R P. What is P? Linear momentum. Mass into velocity. So MVR. Very important equation. L is equal to mvr. And what was V in terms of omega? Omega is equal to V by R, right? So V is equal to omega is equal to V by R. So what is V equal to? R omega. So this is R M R omega. M R square omega. This is equal to I omega. So angular momentum. For a point mass, if they're asking you to find out the angular momentum, you can use this MVR. And if it has a definite shape, like a sphere, like a disc, like a ring, or something like that, you can use equation I omega. Okay. Now, when you talk about angular momentum, one very important point of view from where questions can come for your examination is regarding angular momentum conservation. Now, similar to linear momentum conservation, angular momentum will be conserved if the net external torque acting on an object is zero. I repeat, if the net external torque is zero, the angular momentum will be conserved. Okay, so based on angular momentum conservation, you can write L initial is equal to L final, or you can write I1 omega 1 is equal to I2 omega 2. Okay, we'll deal with questions for this later on. So angular momentum is conserved. When is it conserved? The net external torque acting as zero. The angular momentum will be conserved. Okay, clear? Right. So we have talked about torque. We have talked about angular momentum. Now we are gonna see some analogy between the linear motion and the circular motion. Some more equations. One, work done. What have we learned? F dot S. Right? Here in rotation dynamics, we write it as work done is equal to tau dot theta or d theta. Or you can also write like this: work done is equal to, since I wrote d theta, make theta here, for a small angular displacement, tau d theta. Work done. Similarly, kinetic energy equation. How can you write kinetic energy equation? You know that kinetic energy is equal to half mv square. Here it will be kinetic energy is equal to half I omega square. Half I omega square. I is the moment of inertia and omega is the angular velocity. Also, we can also write like this. This is also equal to L square by 2I. And these are also again very important equation. Kinetic energy is equal to L square by 2I, similar to P square by 2M. You have learned it, work energy power. Okay, so half I omega square or L square by 2I, kinetic energy equation. So we learned about work done, kinetic energy. Now what? Power. Power can be written as power is equal to F dot V, right? So here tau dot omega power. Tau dot omega. So that's the word power. Again, one very important concept we have learned in laws of motion is regarding impulse. What is impulse? A large force acting for a short duration of time. Here again, you can use the concept of impulse here. How do you use it? Impulse. The impulsive impulse is equal to tau delta t, or you can write tau average. Delta t is equal to delta L. What is delta L? Change in angular momentum. So change in angular momentum is equal to the torque into the time duration for which it is acting, right? And we can also apply Newton's second law here and the first law. The laws are also applicable. All the laws are applicable here. So how do you write that? We can write according to that F is proportional to dp by dt, right? Here when you write it, you can write like this. Instead of F torque is equal to dl by dt. Rate of change of angular momentum. Okay. So for all the equations that we have learned in work energy power and in linear motion, we can actually write the corresponding analogous equation here. So for kinetic energy we written, and remember for the theorems, remember about work done, about torque, impulse and everything, please remember that. Okay, so these are the main short equations you have to remember. So we are moving on to the fourth part now. Okay, and that is about rolling motion. Alright, now we are moving on to the fourth portion of the chapter, and that is about rolling motion. Now, when you talk about a rotational motion, three types of motion we will have to analyze. One, a pure translational motion. Translation. Two, spinning motion or a pure rotational motion. And the third one is our rolling motion. So if it is the first, a pure rotational motion means it is actually a motion of an object. It may be a circular object, it may be a square object, it may be a cube, something. It is in a pure translation motion, there is no rotation taking place. Or even if it is a circular object, we expect a circular object to roll on a surface, right? But even if it is a circular object, and if there is no friction, means there is no effective friction, means it will just slip on the surface. It just move like this, slip and move. Just slip and move like this, right? So in a slipping motion or a pure translational motion, we can say that if this is my object and this is undergoing a slipping or a pure translational motion, means at each and every single point we take, the velocity will be v itself. No change in that, because it is a pure slipping motion. Every point on the object will actually be moving with the velocity v itself. There won't be any change there. Now, when you're talking about a rotational motion, it will be spinning on its axis, like the fan we are seeing. It is spinning about its axis, right? So it is spinning about its axis means translational velocity will be equal to 0. There is no straight line motion, there is only a rotational motion, and there is only a spinning motion taking place there. There is no linear motion there. Okay. So here, rotational motion, again, all the points will be v itself without any change if it is a uniform motion. That's okay. And the third one, the rolling motion, or we can call it rolling, we can refer to specifically rolling without slipping. So in rolling motion, what is happening is there will be a translational motion and there is a rotational motion also. There is a translational motion and there is a rotational motion also in case of a rolling motion, right? So what happens here is, here when we take an object here, this is moving forward, right? It has the center of mass has a velocity v forward. Now at this point has a velocity v. So what is the net velocity? V and v will be 2v. Now here at this point, what will be the velocity? It will be root 2v, and for this point it will be equal to 0. The meaning of that statement is, at the point of contact, in case of a rolling without slipping, there is no relative velocity, which means there is no relative motion at the point of contact. And hence we can say that even though friction is responsible for this motion, the energy dissipation or the work done against friction in case of a rolling motion without slipping will be equal to 0. Will be equal to 0. Right? So in case of rolling motion without slipping, the energy dissipation or the work done at the point of contact against friction will be equal to 0. Now, suppose I am taking this object on top of an inclined plane. Okay, I am taking it top of an inclined plane and keeping object here. Keeping it over here. It may be a ring, it may be a disc, it may be a cylinder, it may be a sphere. Now, one thing you have to remember is, if it is just a translational motion, means we can write the kinetic energy would be equal to just half mv squared. But in case of a rotational or a rolling motion, one more term will come there, and that will be the rotational kinetic energy, which I just showed you earlier, that is half I omega square, right? And from here we can actually simplify this expression further. Half I can write it as mk square if you want, or if you know the shape of the object that is rolling down, you can write it as m. If a sphere means 2 by 5 mr square, ring means mr square, similarly you can write it. Omega I'm going to write v square by r square. Fine. So this is equal to half mv square, I'm taking it outside. So remaining as 1 plus k square by r square. So the kinetic energy, I'm writing it as half mv square into 1 plus k square by r square. So when the object is rolling down the inclined plane, it will actually have two kinetic energy associated with it. One will be the translational kinetic energy and the other will be the rotational kinetic energy. Right? So let's find out what is the velocity, the acceleration and the time to reach the bottom. To find that out, it's very simple. We apply the concept of energy conservation. So at this point, it is at a certain height h. What kind of energy does it have? It will have a potential energy, mgh, equal to, when it rolls and comes over here, the entire potential energy will be converted into the kinetic energy, assuming that there is no loss against air resistance and everything, and sound and everything. This will be converted into the kinetic energy. I told you kinetic energy, two parts, which are half m v square into 1 plus k square by r square, the rotational and the translation kinetic energy. So using this concept, you can actually get the equation for the velocity, acceleration and time. Alright, so the velocity equation, and also you'll have to make use of equations for linear motion also there. So the velocity, you'll be getting it as velocity is equal to root of 2gh by 1 plus k square by r square. Acceleration, you will get it as a is equal to g sine theta divided by 1 plus k square by r square. Similarly, the time of descent, you can write as t is equal to 1 by sine theta root of 2h by g 1 plus k square by r square. Now from these three equations, one thing is very clear. The velocity does not depend on theta, which means if the angle of inclination of the inclined plane is theta, velocity does not depend on the angle of inclination. But acceleration and the time depends on theta. Clear? Now, we can say that k square by r square value, I have already shown you how to find k square by r square value, right? So if we know the value of k square by r square, we can determine which, suppose 2 or 3 objects are rolling down the inclined plane at the same time. If we know the value of k square by r square, we can determine which reaches there first. Okay, so let me give you a small hint to remember that. If the moment of inertia of a certain object rolling down the inclined plane is less, then its corresponding k square by r square value will be less for that. Okay, its corresponding k square by r square value will be less. So using that concept, you can easily find out. Okay, say for example, we have 3 objects, maybe we'll take 4 objects, all the 4 together. We have a sphere, we have a ring, we have a cylinder, and a disk. The 4 objects are rolling down an inclined plane. Which will reach the ground first? Which one? Find it out. Which one? Yes, the sphere will be reaching the ground first with a greater velocity and will be reaching first at the bottom. Okay, so for questions like this, we can actually use that concept. Okay, and one more thing worth remembering is, suppose we have a hollow sphere and a solid sphere. Hollow and a solid. As you know, the shape is same for both, right? The shape is same for both. And when these 2 objects are rolling down the inclined plane, which will reach the ground first? It will be a solid sphere which is reaching the ground first. It will be the solid sphere which is reaching the ground first when 2 objects having the same shape rolls down the inclined plane. Here one is hollow, the other is solid, but solid will be reaching first. Okay, so these are the major important points you have to remember. So in rotational dynamics, we have discussed about center of mass concept. We have discussed about moment of inertia concept, or the small equations which are very necessary for your examination point of view. You can actually get one question guaranteed from that portion, okay? From that small equations, a lot of equations have given you. That portion you can expect a question. And the 4th portion, rolling motion, is also a very, very important portion. Okay, so rotational dynamics, once you are familiar with the moment of inertia value, how to locate the center of mass of different objects, and how to find all those things, then the chapter will be all set. Now it's about doing questions and practicing. Okay, so I hope it's clear. So feel free to comment on the chapter, and if you have any specific chapters that you want me to discuss or you want me to take, you can just comment below, and please do subscribe the channel. So signing off, thank you.